right now, as you're watching this video, you exist in a universe that is 13.8 billion years old. Every atom in your body, every photon of light hitting your eyes, every quantum fluctuation in the space around you, all of it can trace its story back to a single moment, the Big Bang. But here's the question that has haunted scientists, philosophers, and curious minds for decades. What was there before that moment? What if I told you that before our universe existed, there might have been infinite other universes? What if our entire reality, everything we've ever known or could ever know, is just one brief chapter in a story that has been playing out for eternity? What if the Big Bang wasn't the beginning, but just the latest beginning in an endless cycle of cosmic death and rebirth? Today, we're going to journey to the very edge of human knowledge and explore the most mind-bending theories about what existed before existence itself. We'll discover universes that collide in dimensions we can't perceive, realities that emerge from absolute nothingness, and cosmic cycles that stretch back infinitely through time. By the end of this exploration, you'll never look at the night sky the same way again. Welcome to what might be the most ambitious journey we'll ever take together. We're going to push against the absolute boundaries of what it means to exist. The story we're about to tell isn't just about physics or cosmology. It's about the deepest questions that consciousness can ask. Where did everything come from? Why is there something rather than nothing? And what does it mean to exist in a universe that might be just one tiny part of something infinitely larger? Now, I want you to do something for me. Take a moment and really think about the fact that you exist. Not just that you're alive, but that there's something rather than nothing at all. That atoms arrange themselves into stars, that stars forge the elements that become planets, that planets can harbour the chemistry that becomes life, and that life can become consciousness capable of pondering its own existence. The chain of events that led to this moment is so improbable, so precise, so extraordinary, that it almost defies comprehension. And yet, here we are. If we compress the entire history of the universe into a single year, with the Big Bang occurring at the stroke of midnight on January 1st, then human civilization wouldn't appear until the last few seconds, before midnight on December 31st. Your entire life would be less than a millisecond in this cosmic calendar. And yet, in that infinitesimally brief moment of cosmic time, human consciousness has managed to peer back toward the very beginning of everything and ask, what came before? The theories we're going to explore today aren't science fiction. They're serious scientific proposals developed by some of the brightest minds in physics and cosmology. Names like Alan Guth, Andre Linde, Neil Turok, Paul Steinhardt, Stephen Hawking, and Roger Penrose. These scientists have dedicated their careers to understanding the deepest mysteries of reality, and their work has led them to propose ideas so strange, so counterintuitive, that they challenge our very notions of what it means for something to exist. We'll start by exploring why asking what came before the Big Bang might be like asking what's north of the North Pole. A question that seems to make sense, but actually reveals something profound about the nature of time itself. Then we'll dive into the major theories. The idea that our universe is part of an eternal cycle of death and rebirth. The possibility that we're just one bubble in an infinite cosmic foam of universes. The mind-bending concept that our reality was born from a collision in higher dimensions we can't even perceive. And we'll discover how some of the greatest minds in physics are proposing that information itself might be more fundamental than matter and energy. By the end of our journey, you'll understand why some scientists think we might be living in a simulation, why others believe consciousness itself plays a role in creating reality, and why the question of what came before the Big Bang might actually be the key to understanding what comes after. Are you ready? Because we're about to embark on a journey that will take us from the quantum foam to the multiverse, from the mathematics of infinity to the philosophy of existence itself. Let's begin. Before we can explore what happened before the Big Bang, we need to confront something that challenges our most basic intuitions about reality: the nature of time itself. When you wake up in the morning, you instinctively understand that there was a before you woke up, before you went to sleep, before yesterday, before last year. Time seems to flow like a river, carrying us from past through present toward future. It's so fundamental to our experience that we rarely question it. But what if time isn't what we think it is? In 1915, Albert Einstein revolutionized our understanding of reality with his theory of general relativity. Einstein showed us that time isn't separate from space. They're woven together into a single fabric called space-time. This fabric can be stretched, compressed, and curved by matter and energy. Near a massive object like a star, time actually runs slower. If you could stand on the surface of the sun, your watch would tick more slowly compared to someone floating in empty space. Time itself is relative, dependent on where you are and how fast you're moving. Now, here's where it gets truly mind-bending. According to our current understanding of cosmology, space-time itself began with the Big Bang. Not just space, not just time, but the very framework that allows before and after to have meaning. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question assumes there's a direction called north beyond the North Pole, but the concept of north loses its meaning at that point. Similarly, the concept of before might lose its meaning at the Big Bang. But this leads us to an even deeper question. If time began with the Big Bang, what does that mean for causality? How can something begin without something causing it to begin? And if there was no time before the Big Bang, how can we even think about what might have existed? This is where the brilliance of modern theoretical physics shines through. Scientists have found ways to think about these questions that don't rely on our everyday intuitions about time and causality. Some theories propose that what we call the Big Bang was actually a transition from one kind of time to another. Others suggest that there are timeless laws of physics that can give rise to time itself. And still others propose that our universe exists in a larger framework where different kinds of time or even timelessness are possible. The key insight is that just because our experience of time began 13.8 billion years ago doesn't mean that reality itself began then. There might be deeper levels of reality operating by different rules that existed before our space-time came into being. Think of it this way. Imagine you're watching a movie. The story of the movie has a beginning, middle, and end within the film's timeline. But the movie exists on a DVD, which exists in a player, which exists in a room, which exists in a world that has its own timeline completely separate from the movie's timeline. Similarly, our universe might be like a movie playing out in a larger reality that operates by completely different rules of time and causation. This understanding opens up fascinating possibilities. Maybe our Big Bang was the start of a new scene in an eternal cosmic drama. Maybe it was the result of processes happening in dimensions we can't perceive. Maybe it emerged from a realm where the very concept of before and after works differently than we imagine. Let's explore these possibilities, starting with one of the most elegant ideas in all of cosmology: the eternal cycle. Imagine the universe as a cosmic heart, beating since the dawn of eternity, expanding, contracting, expanding, contracting, each beat lasting billions of years, each cycle bringing new possibilities, new forms of matter and energy, new chances for complexity and consciousness to emerge. This is the vision of the cyclic universe, and it's one of the most aesthetically beautiful theories about what might have existed before our Big Bang. The idea of cosmic cycles isn't new. Ancient Hindu cosmology spoke of endless cycles of creation and destruction, each lasting billions of years. The ancient Greeks, including philosophers like Heraclitus, proposed that the universe goes through eternal cycles of fire and renewal. But modern cyclic cosmology is far more sophisticated, grounded in cutting-edge physics and mathematics, rather than philosophical speculation. Let's start with the classical version of cosmic cycling. According to this model, our universe will not expand forever. Instead, at some point in the distant Ujian future, perhaps 100 billion years from now, perhaps much longer, the expansion will slow, stop, and reverse. Picture this: galaxies that are currently racing away from each other will start moving back together. The cosmic microwave background radiation, currently stretched thin across the vastness of space, will begin to compress and heat up. Stars will merge, black holes will collide, and everything in existence will start falling back together. As the universe contracts, incredible things will happen. The night sky will grow brighter as galaxies crowd together. Eventually, the temperature will rise so high that atomic nuclei will break apart. Then atoms themselves will be torn to pieces by the intense heat and radiation. In the final moments, before what cosmologists call the Big Crunch, all matter and energy in the universe will be compressed into a region smaller than an atom, smaller than a proton, until it reaches what physicists call a singularity, a point of infinite density and temperature where the known laws of physics break down. And then, according to cyclic theory, something extraordinary happens. The singularity doesn't just sit there, it explodes outward in a new Big Bang, creating fresh space, fresh time, and fresh possibilities for matter and energy to organise themselves into new forms. This isn't just speculation. Some versions of cyclic cosmology are based on serious theoretical physics, including modifications to Einstein's general relativity and insights from quantum mechanics. One of the most sophisticated modern versions was developed by physicists Paul Steinhardt and Neil Turok. Their model doesn't rely on a violent Big Crunch. Instead, it proposes that our universe is one of two three-dimensional surfaces, called branes, floating in a higher dimensional space. Picture two sheets of paper floating parallel to each other. Periodically, these sheets come together and collide. Each collision creates what we observe as a Big Bang, generating new matter and energy and setting the stage for a new cosmic cycle. This connects to what's called the ekpyrotic model, from the Greek word meaning conflagration or renewal by fire. In this version, the collision between branes doesn't destroy the previous universe, but transforms it, recycling its information and energy into a new cosmic configuration. If cyclic cosmology is correct, then our Big Bang 13.8 billion years ago wasn't the absolute beginning of everything. It was just the most recent beginning in an infinite series of cosmic rebirths. Before our universe, there was another universe that lived its full life, developed its own galaxies and stars and planets, perhaps its own forms of life and consciousness. That universe eventually contracted or collided with another brain, dying so that ours could be born. And before that universe, another and another, stretching back through infinite time, an eternal succession of cosmic generations, each potentially different from the last. This raises profound questions about identity and meaning. If there have been infinite previous universes, then everything that has ever happened in our universe has probably happened before in some previous cycle. Every conversation you've ever had, every thought you've ever thought, every moment of joy or sorrow, all of it might have occurred countless times in previous cosmic cycles. Some versions of cyclic cosmology suggest that each cycle is slightly different, with the fundamental constants of physics shifting slightly from one universe to the next. In some cycles, gravity might be stronger, making it impossible for large structures to form. In others, the electromagnetic force might be weaker, preventing atoms from holding together. Our universe, with its particular set of physical laws that allow for the formation of stars, planets and life, might be just one note in an infinite cosmic symphony. But cyclic cosmology faces a significant challenge: the second law of thermodynamics. This law states that entropy, roughly speaking, disorder, always increases over time. If the universe has been cycling for infinite time, why hasn't it reached a state of maximum entropy, where no further change is possible? Different cyclic models propose different solutions to this problem. Some suggest that each cycle somehow resets the entropy, starting fresh with each new Big Bang. Others propose that the total entropy continues to increase, but each cycle creates new space where low entropy structures can form. Another challenge for cyclic cosmology is observational evidence. If our universe has been through previous cycles, we might expect to find some trace of those previous incarnations, but our observations show a universe that appears to have emerged from a hot, dense, uniform state with no obvious signs of pre-existing structure. However, some cyclic theorists argue that the violent process of cosmic recycling would erase most traces of previous cycles, like a cosmic reset button that clears the slate for each new universe. Despite these challenges, cyclic cosmology offers a profound perspective on our place in existence. If this theory is correct, then we're part of a story that has no beginning and no end. Death is not final, not for individuals necessarily, but for the cosmic process itself. The universe dies and is reborn, over and over, forever. In this view, existence itself is eternal, and our particular cosmic moment is just one movement in an infinite cosmic dance. As we'll see in our next section, there's another way to think about eternity and infinity, one that doesn't require our universe to die and be reborn, but instead suggests that new universes are being born all around us, constantly, in a process that never stops. What if our entire observable universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, is just a tiny bubble floating in an infinite ocean of other universes? This is the mind-bending possibility suggested by eternal inflation theory, one of the most widely accepted ideas in modern cosmology, and it provides a completely different answer to the question of what existed before our Big Bang. To understand eternal inflation, we first need to understand regular inflation. In the early 1980s, physicist Alan Guth was trying to solve several puzzles about our universe. Why does space appear to be so flat? Why is the temperature of the cosmic microwave background so uniform across the sky? Why don't we see certain exotic particles that early universe theories predicted? Guth's solution was elegant. What if the universe underwent a period of incredibly rapid expansion in its first fraction of a second? Not just rapid, exponential. During this inflationary period, the universe would have doubled in size every tiny fraction of a second. To get a sense of how dramatic this expansion was, imagine a balloon that doubles in size every second. After 1 second, it's twice as big. After 2 seconds, 4 times as big. After 10 seconds, it's over 1,000 times larger. After just 60 seconds of this doubling, the balloon would be over 1 billion times its original size. Now, imagine that instead of doubling every second, the universe doubled in size every 10 to the negative 35 seconds. And instead of lasting 60 seconds, this process continued for about 10 to the negative 32 seconds. In that tiny fraction of a second, much shorter than the time it takes light to cross a proton, the universe expanded by a factor that's hard to even write down. A region smaller than a subatomic particle inflated to become larger than a basketball, and possibly much larger. This inflationary expansion explains many features of our observable universe. But here's where it gets truly extraordinary. What if inflation didn't just happen once and then stop? What if it's still happening? Everywhere, all the time. This is the core insight of eternal inflation theory, developed by physicists like Andrei Linde and Alexander Vilenkin. According to this theory, inflation is the natural state of the cosmos. It's what space does when left to itself. The driving force behind eternal inflation is a quantum field called the inflaton field. Picture this field as an invisible energy that fills all of space. In most regions, this field has a high value, causing rapid inflationary expansion, but occasionally, through quantum fluctuations, the field can randomly drop to a lower value in small patches. When this happens, inflation stops in that region, and the energy of the inflaton field gets converted into matter and radiation, creating what we observe as a Big Bang. The hot, dense state that our universe emerged from wasn't the absolute beginning of everything. It was just the moment when inflation stopped in our particular patch of the larger cosmic fabric. Think of our entire observable universe as a bubble that formed when inflation stopped in our region. But outside our bubble, inflation continues, constantly creating new space. And within this inflating space, new bubbles are constantly forming as the inflaton field randomly drops to lower values in different patches. Each bubble becomes its own universe, with its own Big Bang, its own physical laws, its own galaxies and stars and planets. Some of these universes might be similar to ours, others might be radically different, with different numbers of dimensions, different fundamental forces, different possibilities for matter and structure. The scale of this multiverse is truly staggering. Our observable universe, everything we can see with our most powerful telescopes, is about 93 billion light years across. But the total size of our bubble universe might be much larger, possibly infinite, and our bubble is just one among an infinite number of bubbles in the eternal inflation multiverse. New universes are being created constantly, emerging from the quantum fluctuations in the inflating space around us. This leads to what physicists call the landscape of possible universes. In our universe, the electron has a particular mass, gravity has a particular strength, and space has 3 dimensions. But in other bubble universes, these fundamental parameters might be different. String theory, our best attempt at a theory of everything, suggests that there might be 10 to the 500 different possible ways to configure the fundamental laws of physics. That's a number so large that if you wrote it out, it would contain more digits than there are atoms in our observable universe. If eternal inflation is correct, then every single one of these possible configurations might be realized somewhere in the multiverse. There would be universes where gravity is much stronger, causing stars to form and die in minutes rather than billions of years. Universes where the electromagnetic force is weaker, making atoms impossible. Universes with different numbers of spatial dimensions, where the very geometry of space is alien to our experience. This raises a profound question. Why do we find ourselves in a universe that's suitable for life? The answer might be surprisingly simple. We exist in this universe precisely because it's one of the rare ones where life is possible. In the vast majority of bubble universes in the multiverse, the physical laws don't allow for the formation of complex structures like stars, planets, or living organisms. We don't observe those universes because there's no one there to observe them. This is called the anthropic principle. The idea that we observe a life-friendly universe, not because the universe was designed for life, but because we can only exist in universes where life is possible. So what existed before our Big Bang? According to eternal inflation theory, there was the eternal inflation field, constantly expanding and creating new space. Quantum fluctuations were causing inflaton field values to drop randomly, creating bubble universes throughout this expanding space. At some point, a quantum fluctuation occurred in our region, causing inflation to stop and our universe's Big Bang to begin. But this was just one event among countless others happening throughout the multiverse. Before our universe began, other universes were already forming, evolving, and possibly dying. The multiverse itself has no beginning. It's eternal, constantly creating new realities through the process of eternal inflation. One of the strangest aspects of the multiverse is that we can never make contact with other bubble universes. The space between bubbles is expanding faster than light, so no signal from another universe could ever reach us, and no signal from our universe could ever reach them. In a sense, each bubble universe is causally isolated from all the others. We might be surrounded by an infinite number of other realities, some containing their own forms of life and consciousness, but we'll never be able to communicate with them or even detect their existence directly. This raises the question, if we can't observe other universes directly, how can we test the theory of eternal inflation? Scientists have proposed several possible ways to find indirect evidence. One possibility is to look for patterns in the cosmic microwave background radiation that might be caused by collisions between our bubble and neighbouring bubbles in the very early universe. Another is to look for statistical patterns in the distribution of galaxies that might reflect the quantum fluctuations that gave rise to our universe. So far, the evidence is suggestive, but not conclusive. We have good reasons to think inflation occurred in our universe's early history, but whether this inflation is eternal, and whether it creates a multiverse of bubble universes remains an open question. The multiverse raises profound philosophical questions about the nature of existence and reality. If there are infinite universes, then everything that can happen will happen somewhere. There would be universes almost identical to ours, but with tiny differences. Perhaps in one, you chose a different career, or dinosaurs never went extinct, or the fundamental constants are slightly different. Some philosophers argue that the multiverse makes existence less special. If everything happens somewhere, then nothing is unique or meaningful. Others argue that it makes existence more wondrous, that consciousness and life and beauty emerge naturally from the infinite creativity of the cosmos. Whether you find it comforting or disturbing, the multiverse presents a vision of reality as eternally creative. Before our Big Bang, the cosmos was already creating new universes. During our cosmic history, it has continued creating them, and long after, our universe has expanded into cold, empty darkness. The eternal inflation field will still be creating new bubbles of space and time, new possibilities for matter and consciousness to emerge. In this view, existence itself is not just eternal, but eternally creative, constantly exploring new ways for reality to unfold. But there's yet another possibility for what might have existed before our Big Bang, one that takes us into even stranger territory, where our three-dimensional universe is just a shadow of a higher dimensional reality. Imagine that our entire three-dimensional universe, everything we can see, touch, or measure, is actually just the surface of a higher dimensional object, like a shadow cast by something far more complex than we can directly perceive. This is the startling possibility suggested by the ekpyrotic model, named after the ancient Greek concept of cosmic renewal through fire. But instead of literal fire, this theory proposes that our universe was born from a collision between vast, higher dimensional objects called brains. To understand the ekpyrotic model, we first need to wrap our minds around the concept of extra dimensions. We're accustomed to thinking of space as having three dimensions: length, width, and height. We can move forward and backward, left and right, up and down. These three dimensions plus time make up the four-dimensional space-time that we experience. But mathematics and physics suggest that reality might have more dimensions than we can directly perceive. String theory, our most ambitious attempt to unify all the forces of nature, requires space to have 10 or 11 dimensions in total. So where are these extra dimensions? One possibility is that the extra dimensions are compactified, curled up so small that we can't detect them. Imagine looking at a garden hose from a great distance. It appears to be a one-dimensional line, but if you get close enough, you can see that it actually has a circular cross-section. The circular dimension was always there, but it was too small to notice from far away. Similarly, what we perceive as three-dimensional space might actually have additional dimensions curled up at every point. But these dimensions are so small, perhaps at the scale of the Planck length, which is 10 to the power of negative 35 meters, that we can't directly observe them. The ekpyrotic model takes a different approach to extra dimensions. Instead of hiding them by making them small, it suggests that we're confined to a three-dimensional surface, called a brain, short for membrane, floating in a higher dimensional space called the bulk. Think of this analogy. Imagine you're a two-dimensional being living on the surface of a sheet of paper floating in three-dimensional space. You can move around on the surface of the paper, but you can't move up or down off the paper. From your perspective, the world has only two dimensions, even though the paper itself exists in three-dimensional space. According to brain world models, we might be like those two-dimensional beings, except we're three-dimensional beings, confined to a three-dimensional brain, floating in higher dimensional space. All the matter and energy we're familiar with, atoms, light, forces, might be restricted to our brain, while gravity can propagate through the higher dimensional bulk. Now comes the truly remarkable idea at the heart of the ekpyrotic model. What if our Big Bang wasn't the creation of space and time from nothing, but rather the result of a collision between our brain and another brain floating nearby in the higher dimensional bulk? Picture two sheets of paper floating parallel to each other in three-dimensional space. Now imagine that one sheet slowly drifts toward the other until they collide. The collision would release enormous amounts of energy across the entire surface of both sheets. In the ekpyrotic model, this collision between brains is what we observe as the Big Bang. The tremendous energy released by the collision created the hot, dense state from which our universe emerged. But both brains existed before the collision, potentially for a very long time. The ekpyrotic model, developed by physicists Neil Turok, Paul Steinhardt and their collaborators, provides a detailed scenario for how this collision might occur. Initially, two brains float in the higher dimensional bulk, separated by a small distance. There's an attractive force between them, analogous to gravity, but operating in the extra dimensions. This force causes the brains to accelerate toward each other. As they approach, the space between them shrinks, and the fields living on the brains become more and more energetic. The collision itself is incredibly violent from our perspective. It's the event we call the Big Bang. But from the perspective of someone who could see the entire higher dimensional space, it's simply two membranes coming into contact with each other. This gives us a very specific answer to the question of what existed before the Big Bang. Before the collision, there were two brains floating in higher dimensional space. These brains might have existed for an extremely long time, possibly forever, before the conditions were right for them to collide. On one of these brains, the conditions were such that when the collision occurred, it created a universe with physical laws suitable for the formation of matter, stars, galaxies, and eventually life. That's the brain we live on now. But what about the other brain? The ekpyrotic model suggests that it might have its own physics, its own matter, its own forms of organisation. There might have been an entirely different universe existing on that brain before the collision, with its own history, its own complexities, its own possibilities for consciousness. Some versions of the ekpyrotic model suggest that this process is cyclical. After the collision, the two brains might separate again, move apart in the higher dimensional space, and then eventually come back together for another collision. This would create a cyclical universe, similar to what we discussed earlier, but with a very different mechanism. Instead of our universe expanding and then contracting, the cycle is driven by the periodic collisions between brains in higher dimensional space. Each collision would create a new Big Bang, resetting our universe and beginning a fresh cycle of cosmic evolution. Between collisions during the long periods when the brains are separating and then approaching each other again, our universe would evolve, form galaxies and stars, and perhaps develop life and consciousness. One of the most intriguing aspects of the ekpyrotic model is how it explains the apparent flatness and uniformity of our universe. In standard Big Bang cosmology, the universe appears to be remarkably flat and smooth, which requires very special initial conditions. In the ekpyrotic model, this flatness and smoothness arise naturally from the collision process. As the two brains approach each other, any irregularities in their surfaces get smoothed out by the attractive forces between them. When they collide, they create a universe that's naturally flat and uniform. This solves what cosmologists call the flatness problem and the horizon problem, without requiring the rapid inflationary expansion that we discussed in the previous section. One of the challenges for the ekpyrotic model is finding ways to test it observationally. Since the collision occurred nearly 14 billion years ago, we need to look for subtle signatures in the cosmic microwave background radiation or the distribution of galaxies that might distinguish the ekpyrotic scenario from other models. The ekpyrotic model makes specific predictions about the pattern of temperature fluctuations in the cosmic microwave background. These fluctuations are slightly different from what we'd expect in standard inflationary cosmology, providing a potential way to test the theory. Current observations are not precise enough to definitively distinguish between different models, but future experiments might be able to detect the subtle signatures that would confirm or rule out the ekpyrotic scenario. Perhaps the most mind-bending aspect of the ekpyrotic model is the implication that there might be another three-dimensional universe existing parallel to ours in the higher dimensional bulk. If the collision that created our Big Bang involved two brains, and if both brains survived the collision, then there might be another universe with its own three-dimensional space, its own matter and energy, its own galaxies and stars, existing just a tiny distance away from us in the extra dimensions. This parallel universe would be completely inaccessible to us because we're confined to our brain and can't move through the higher dimensional bulk. Light and matter from our universe can't cross over to the other brain, and light and matter from their universe can't reach us. But gravity, which can propagate through the bulk, might provide a subtle connection between the two universes. Some physicists have speculated that certain anomalies in our universe's gravitational behaviour might be evidence of gravitational influences from this parallel brain. If there can be two brains in the higher dimensional bulk, why not more? Some versions of brain cosmology suggest that the bulk might contain many brains, each hosting its own three-dimensional universe. These brains might occasionally collide with each other, creating big bangs and giving birth to new universes. Or they might exist in isolation, separated by vast distances in the extra dimensions, each evolving according to its own physical laws. This creates a different kind of multiverse from the one we discussed in the eternal inflation section. Instead of bubble universes created by quantum fluctuations in an inflating field, we have brain universes floating in higher dimensional space, occasionally interacting through collisions or gravitational influences. The ekpyrotic model raises profound questions about the nature of reality and our place within it. If we live on a three-dimensional brain floating in higher dimensional space, then most of reality is literally beyond our reach. We can only interact with the tiny fraction of the cosmos that exists on our particular brain. This is a humbling perspective. It suggests that our universe, vast as it seems to us, might be just a thin slice of a much larger and more complex reality. The three dimensions of space that define our entire experience might be like the surface of a vast ocean, while the true depth of reality extends in directions we can't even imagine. If there are other brains with their own forms of matter and energy, is it possible that some of them have developed their own forms of consciousness? Could there be thinking beings on parallel brains, living in universes with different physical laws, contemplating their own versions of the question we're asking? What existed before their Big Bang? The ekpyrotic model suggests that the answer might be yes. If consciousness can emerge from the complex organisation of matter and energy on our brain, it might emerge on other brains as well, taking forms we can't even imagine. But perhaps the most radical possibility of all is that we don't need pre-existing brains or inflating fields or cyclical processes. Perhaps the universe can literally create itself from nothing at all. Not from empty space, but from true, absolute nothingness. This brings us to our next theory, one that challenges our most basic assumptions about existence itself. What if I told you that the most natural thing in the cosmos isn't the existence of something, but the existence of everything? What if the reason our universe exists isn't because something created it, but because nothingness is actually unstable? This is perhaps the most mind-bending idea in all of cosmology. The possibility that our entire universe spontaneously created itself from absolutely nothing through the bizarre laws of quantum mechanics. Before we can understand how something can come from nothing, we need to be very precise about what we mean by nothing. In everyday language, when we say there's nothing in a room, we usually mean it's empty of furniture or people. But the room still contains air, light, electromagnetic fields, and the quantum vacuum. Even if we removed all the air and blocked out all the light, the room would still contain space itself, the three-dimensional arena in which things can exist. And according to quantum mechanics, empty space is never truly empty. It's buzzing with activity, filled with quantum fields that create virtual particles that pop in and out of existence constantly. But the nothing we're talking about in quantum creation theory is far more radical. It's not just empty space, it's the absence of space itself. No dimensions, no time, no fields, no laws of physics. Absolute, total nothingness. To understand how something can emerge from this absolute nothingness, we need to understand the strange behaviour of the quantum vacuum, the state of lowest possible energy in quantum field theory. You might think that the lowest energy state would be completely static, with nothing happening at all. But quantum mechanics tells us something remarkable. Even in the vacuum, quantum fields are constantly fluctuating. Virtual particles appear in pairs, exist for incredibly brief moments, and then annihilate each other and disappear. These aren't just theoretical constructs. Virtual particles have real, measurable effects. They cause what's called the Casimir effect, where two metal plates placed very close together in vacuum will experience a tiny attractive force due to quantum fluctuations. They also cause the slight shift in energy levels of atoms that we can measure with incredible precision. Quantum mechanics also gives us the concept of quantum tunneling, the ability for particles to appear on the other side of energy barriers that they classically shouldn't be able to cross. A particle can borrow energy from the vacuum, use it to cross an impossible barrier, and then pay the energy back so quickly that the transaction can't be detected. This happens because quantum mechanics is fundamentally probabilistic. Instead of definite positions and energies, particles have probability waves that describe the likelihood of finding them in different states. These probability waves can extend into classically forbidden regions, making impossible things occasionally possible. Building on these quantum mechanical principles, physicists Stephen Hawking and James Hartle proposed what's called the no-boundary proposal for the origin of the universe. According to their theory, asking what came before the Big Bang is like asking what's south of the South Pole. The question doesn't make sense, because before doesn't exist. But more than that, they suggested that the universe could spontaneously appear from nothing through a quantum tunneling event. Just as a virtual particle can borrow energy and briefly exist before paying it back, the entire universe could borrow the energy needed for its creation from the quantum vacuum, and then pay it back through its subsequent expansion and evolution. The mathematics behind this idea are extraordinarily complex, involving concepts from quantum field theory, general relativity, and mathematical physics that push the boundaries of human understanding. But the basic idea can be expressed relatively simply. In quantum mechanics, everything that can happen has some probability of happening. The probability might be incredibly small, but it's never zero. Even the spontaneous appearance of a universe from absolute nothingness has some tiny but finite probability. Given enough time, or in the case of absolute nothingness, given the timeless quantum realm where all possibilities exist simultaneously, even events with infinitesimally small probabilities will eventually occur. Hawking and Hartley described the creation of the universe using what they called the wave function of the universe, a mathematical description of all possible universes and their relative probabilities. According to their calculations, universes with certain properties, including our own, have higher probabilities of spontaneously appearing than others. This wave function exists outside of time and space, in a realm of pure mathematical possibility. It doesn't require a creator or a pre-existing framework. It simply describes what can exist and with what probability. When a particular possibility becomes actualized, when a universe spontaneously appears, time and space begin, and the classical laws of physics start to apply. But the underlying quantum wave function remains timeless and eternal, constantly generating new possibilities for existence. Physicist Lawrence Krauss popularized a version of this idea in his book, A Universe from Nothing, though his concept of nothing is somewhat different from the absolute nothingness we've been discussing. Krauss focuses on how the known laws of physics, particularly quantum mechanics and gravity, can explain how our universe could arise from an empty but pre-existing space. According to Krauss, the total energy of the universe might actually be zero. The positive energy contained in matter and radiation is exactly balanced by the negative gravitational potential energy of the universe's structure. If the total energy is zero, then the universe could appear spontaneously without violating the conservation of energy. But this raises a deeper question. If the universe created itself through the laws of quantum mechanics, where did those laws come from? How can the laws of physics exist before the physical universe exists? Some physicists argue that the laws of physics are not things that exist in the same way that matter and energy exist. Instead, they're descriptions of the logical relationships that must hold between any possible physical entities. In this view, the laws of physics are necessary truths, like mathematical theorems that don't require a physical substrate to exist. Others suggest that there might be deeper, more fundamental principles that give rise to both the laws of physics and the physical universe itself. These principles would exist in a realm of pure logic or mathematical necessity, beyond the distinction between existence and non-existence. If universes can spontaneously appear from nothing through quantum processes, then many different kinds of universes should appear, each with different physical laws and constants. The vast majority of these universes would be unsuitable for the formation of complex structures like galaxies, stars, planets, and life. We observe a life-friendly universe, not because such universes are the most probable, but because we can only exist in universes where life is possible. This is another application of the anthropic principle we discussed in the multiverse section. In this quantum creation scenario, there would be countless universes appearing spontaneously from nothing, but only in the rare ones, with suitable physical laws, would conscious observers evolve to ask questions about their own existence. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in determining which quantum possibilities become actualized. If this is true, then the emergence of consciousness in our universe might not just be a byproduct of physical processes, but an essential part of what makes the universe real. This leads to some very strange possibilities. Maybe universes only become fully actualized when consciousness evolves within them to observe and measure their properties. Maybe the act of conscious observation is what collapses the wave function of the universe and makes it definitively real, rather than just a quantum superposition of possibilities. This is highly speculative, and most physicists don't accept the idea that consciousness plays such a fundamental role in physics, but it illustrates how quantum creation theory pushes us to question our most basic assumptions about the nature of reality, existence, and the role of conscious observers in the cosmos. If quantum creation is correct, then nothingness is incredibly creative. Far from being static or empty, the state of absolute nothingness is constantly generating new universes, new possibilities, new ways for existence to unfold. This process has no beginning and no end. It's not that nothingness existed for a while and then decided to create our universe. Rather, the quantum creation process is eternal and ongoing. Universes are constantly appearing spontaneously from nothing, each with its own space, time, and physical laws. Before our Big Bang, there was absolute nothingness, but this nothingness was not empty or static. It was full of potential, pregnant with infinite possibilities for existence. Our universe is just one of these possibilities that happened to become actualized through a quantum tunneling event 13.8 billion years ago. Quantum creation theory raises profound philosophical questions about the nature of existence itself. If something can truly come from nothing, then existence doesn't require explanation in terms of prior causes. The universe doesn't need a creator or a pre-existing framework. It can simply be a brute fact, a quantum event that happened, because quantum events can happen. This might seem unsatisfying to those who want a deeper explanation for why anything exists at all, but it's consistent with a general lesson of quantum mechanics. At the most fundamental level, reality is probabilistic rather than deterministic. Things happen not because they must happen, but because they can happen. One of the major challenges facing quantum creation theory is that it's incredibly difficult to test experimentally. How do you design an experiment to detect the spontaneous creation of universes from nothing? How do you verify that absolute nothingness can give rise to something? Some physicists argue that this makes quantum creation theory more philosophy than science. If a theory can't be tested or falsified, they argue, then it's not really a scientific theory at all. Others contend that the theory makes testable predictions about the properties our universe should have if it was created through quantum tunneling. These predictions can potentially be tested through precise measurements of the cosmic microwave background radiation and other cosmological observations. If quantum creation theory is correct, then our universe is the ultimate bootstrap paradox. It created itself, brought itself into existence through its own quantum mechanical laws, and then evolved to become complex enough to support conscious observers who could discover and understand the process by which it was created. This is a deeply strange and recursive picture of reality. The universe creates itself, evolves consciousness, which then discovers that the universe created itself. It's a closed loop of causation that has no external explanation or justification. It simply is. Whether this picture is ultimately correct remains to be seen, but it represents one of the most radical and challenging ideas in all of science, that existence itself might require no explanation beyond the strange, probabilistic laws that govern the quantum realm. As we'll see in our final major section, there are even more exotic possibilities for what might have preceded our Big Bang. Ideas that challenge not just our understanding of physics, but our understanding of the very nature of reality and information. What if everything we've discussed so far, matter, energy, space, time, quantum fields, is not fundamental? What if, at the deepest level, reality is made not of stuff, but of information? And what if our universe, and whatever came before it, is actually a kind of cosmic computation? This brings us to some of the most radical and speculative ideas about the nature of existence. Theories that suggest the boundary between physics and information theory, between the real and the simulated, might not be as clear as we think. The idea that the universe might be fundamentally computational isn't entirely new. As early as the 1960s, physicist Edward Fredkin proposed that reality might be a kind of cellular automaton, a simple computational process that generates complex patterns through the repeated application of basic rules. More recently, physicists like John Wheeler have suggested that reality is fundamentally informational. Wheeler coined the phrase "it from bit," suggesting that everything, every particle, every force, every property of the universe emerges from yes-no answers to binary questions. In other words, the universe might be made of information in the same way that a digital computer is made of bits. One version of this idea, called digital physics, proposes that space and time are not continuous but are made up of tiny, discrete units, pixels of reality, if you will. Just as a digital image is made up of individual pixels, each with a specific colour value, the universe might be made up of individual space-time pixels, each with specific informational content. In this view, the laws of physics are actually computational rules that determine how the information in each pixel updates from one moment to the next, based on the information in neighbouring pixels. The entire evolution of the universe becomes a vast computational process, calculating each moment of reality from the previous moment. Stephen Wolfram, creator of the Mathematica software and author of A New Kind of Science, has explored this idea extensively. He's shown how simple computational rules can generate incredibly complex patterns and behaviours, patterns that look remarkably similar to the structures we observe in nature. Perhaps the most famous version of the computational universe idea is the simulation hypothesis, popularised by philosopher Nick Bostrom. According to this hypothesis, our entire universe might be a computer simulation running on some advanced civilization's technology. Bostrom's argument is surprisingly logical. If civilizations can become technologically advanced enough to run detailed simulations of entire universes, including conscious beings within those universes, then they would likely run many such simulations. This means there would be far more simulated consciousnesses than real ones. If you accept that premise, then the probability that any given conscious being, including you, is in a simulation rather than a real universe becomes very high. We might all be characters in an incredibly sophisticated video game, or scientific simulation running on some cosmic computer. If our universe is indeed a simulation, then what existed before our Big Bang would be the civilization and technology that created the simulation. The Big Bang would simply be the moment when the simulation was initialized, when the cosmic computer was turned on and began running the program that generates our reality. This gives us a completely different perspective on pre-Big Bang existence. Instead of quantum fields, or colliding brains, or cyclical universes, there would be programmers and computers operating according to technologies and motivations we can barely imagine. The civilization running our simulation might itself be simulated by an even more advanced civilization, leading to an infinite hierarchy of simulated realities. Or they might exist in some base reality that operates according to completely different principles than the simulated physics we observe. Another radical idea comes from neuroscientist Giulio Tononi's Integrated Information Theory, ICARS-IT, which attempts to explain consciousness in terms of information integration. According to IIT, consciousness arises when a system integrates information in a unified, irreducible way. Some philosophers and physicists have extended this idea to suggest that consciousness might be a fundamental feature of reality, present wherever information is integrated, not just in brains, but in any sufficiently complex information processing system. If this is true, then the universe itself might be conscious, constantly integrating the information contained in its quantum fields and particles. The Big Bang might have been the moment when this cosmic consciousness first awakened, beginning the process of self-organization and self-discovery that we observe as the evolution of the universe. This connects to an ancient philosophical idea called panpsychism, the notion that consciousness is a fundamental property of all matter, like mass or electric charge. Instead of consciousness emerging from complex arrangements of unconscious matter, panpsychism suggests that even elementary particles have some rudimentary form of experience. If panpsychism is correct, then the question of what existed before the Big Bang becomes a question about the evolution of cosmic consciousness. Perhaps there was some form of primordial consciousness that decided, in some sense, to organize itself into the pattern we observe as our universe. This is highly speculative, and most scientists are skeptical of panpsychist ideas. But as we struggle to understand the hard problem of consciousness, how subjective experience arises from objective physical processes, some researchers are beginning to take these ideas more seriously. Modern physics has revealed deep connections between information theory and fundamental physics. The holographic principle derived from studies of black holes suggests that all the information in a three-dimensional volume can be encoded on its two-dimensional boundary. This has led some physicists to propose that our three-dimensional universe might actually be a holographic projection of information stored on a two-dimensional surface at the cosmic boundary. In other words, everything we perceive as solid, three-dimensional reality might be a kind of cosmic hologram. If the holographic principle is correct, then what existed before the Big Bang might be the two-dimensional information structure that encodes our three-dimensional universe. The Big Bang would be the moment when this information began to be projected as a holographic reality. Physicist Max Tegmark has proposed what he calls the mathematical universe hypothesis, the idea that our physical reality is a mathematical structure, not that our universe can be described by mathematics, but that it literally is mathematics. According to Tegmark, all mathematical structures that are complex enough exist as physical realities. Our universe corresponds to one particular mathematical structure, while other mathematical structures correspond to other universes with different physical laws. In this view, what existed before our Big Bang was the eternal realm of mathematical structures, a Platonic realm of pure mathematics where all possible realities exist timelessly. Our universe came into being not through a physical process, but through the actualization of a particular mathematical possibility. Some interpretations of quantum mechanics suggest that the act of observation plays a crucial role in determining what becomes real. John Wheeler proposed the concept of a participatory universe, one where conscious observers don't just passively observe reality, but actively participate in its creation. If this is true, then the emergence of consciousness in our universe might be what makes the universe fully real. Before conscious observers evolved, the universe might have existed only as a superposition of quantum possibilities. The Big Bang might represent the moment when these possibilities began to collapse into definite realities through some primordial form of observation or measurement. This suggests that consciousness and physical reality might be more intimately connected than we typically assume. Instead of consciousness being a late addition to an already existing universe, it might be a necessary component of what makes the universe exist at all. If reality is fundamentally informational or computational, what does this mean for human free will and the meaning of existence? If we're characters in a simulation, are our choices real? If the universe is deterministic computation, is there any room for genuine agency and responsibility? These questions push us beyond physics into philosophy, ethics, and theology. Different people will answer them differently based on their values and beliefs, but they illustrate how questions about the origin of the universe inevitably lead us to questions about our own nature and purpose. Some find the computational view of reality comforting. It suggests that consciousness and information are fundamental features of the cosmos, not accidental byproducts of blind physical processes. Others find it alienating, reducing the beauty and mystery of existence to mere data processing. Like all the theories we've discussed, computational and informational models of the universe face significant challenges. Many physicists argue that these theories are too vague to be scientifically useful. They make few specific, testable predictions about observable phenomena. There's also the question of what provides the computational substrate. If the universe is a computer, what is doing the computing? If it's information all the way down, what processes this information and determines how it evolves? Some theorists propose that the computational process might be self-sustaining, that the universe computes itself with no external computational substrate required. But this seems to push the explanatory problem back one level without really solving it. Despite these challenges, some researchers are actively looking for signatures that might indicate whether our universe has computational or informational foundations. These could include discrete rather than continuous structures at the smallest scales, glitches or artifacts that might indicate computational limits, statistical patterns in cosmic data that resemble those produced by algorithmic processes, fundamental limits on information processing or storage in physical systems. So far, no definitive evidence has been found for any of these signatures, but the search continues, driven by the recognition that information theory and computation play increasingly important roles in our understanding of physics. One particularly intriguing possibility is that consciousness itself played a role in the creation of the universe. If consciousness is fundamental and has the power to collapse quantum possibilities into definite realities, then perhaps the Big Bang represents the moment when some primordial form of consciousness chose to actualize our particular universe from among all possible universes. This doesn't necessarily require a supernatural creator. The consciousness involved might be a natural feature of information integration at cosmic scales, or it might emerge from the collective observations of future conscious beings through some kind of retrocausal influence. While highly speculative, this idea offers a vision of the universe as actively creative rather than passively mechanistic, a cosmos where consciousness and physical reality co-create each other in an ongoing process of mutual specification. This brings us to our final section, where we'll step back and consider what all these theories tell us about the nature of existence and our place within it. As we've journeyed through these remarkable theories about what might have existed before the Big Bang, we've encountered ideas that challenge our most fundamental assumptions about reality itself: infinite cycles, endless multiverses, higher dimensional collisions, quantum creation from nothingness, computational realities. Each theory opens up vistas of possibility that stretch our imagination to its limits. But now we need to step back and ask some deeper questions. What do these theories really tell us about the nature of existence? How should they change the way we think about ourselves and our place in the cosmos? And perhaps most importantly, what are the limits of what we can ever truly know about these ultimate questions? One thing you might have noticed as we explored these theories is that each one, in its own way, pushes the question of ultimate origin back one level, without necessarily resolving it completely. If our universe is part of an eternal cycle, we can ask, why does the cycling process itself exist? If we're in a multiverse created by eternal inflation, what explains the existence of the inflation field and the quantum laws that govern it? If our universe emerged from a collision between brains, what explains the existence of the higher dimensional space that contains those brains? Even the most radical theory, quantum creation from nothing, assumes the existence of quantum mechanical laws that allow something to emerge from nothing. Where do those laws come from? This is known as the problem of infinite regress. Every explanation seems to require something else that also needs explaining. We can push the explanation back further and further, but do we ever reach a final, self-explanatory foundation? Perhaps the deepest question isn't what came before the Big Bang, but rather, why is there something rather than nothing at all? This question goes beyond physics and cosmology into the realm of pure metaphysics, the study of what it means for anything to exist. Some philosophers argue that existence itself is the fundamental mystery, and that all our scientific theories, no matter how sophisticated, can only explain how existing things behave and interact. They cannot explain why there are existing things in the first place. The philosopher Ludwig Wittgenstein expressed this sentiment when he wrote, "Not how the world is the mystical, but that it is." The mystery isn't in the details of how reality operates, but in the bare fact that there is a reality to operate at all. Throughout our exploration, we've encountered the anthropic principle, the idea that we observe a universe capable of supporting life precisely because we can only exist in such a universe. This principle appears in different forms across multiple theories, from the multiverse to quantum creation to cyclical cosmology. But the anthropic principle raises profound questions about the relationship between observers and reality. Are we simply lucky to find ourselves in a universe that happens to support life? Or does our presence as observers play a more fundamental role in determining which kind of universe becomes actualized? Some interpretations of quantum mechanics suggest that conscious observation is necessary to collapse quantum possibilities into definite realities. If this is true, then the evolution of consciousness in our universe might not be accidental but necessary, a required component of the process that makes reality real. This doesn't necessarily imply design or purpose in the traditional sense, but it does suggest that consciousness and physical reality might be more intimately connected than our everyday experience suggests. Another theme that runs through many of these theories is the fundamental role of mathematics. Whether we're talking about the equations that govern cosmic inflation, the geometry of higher dimensional branes, or the wave functions that describe quantum creation, mathematics appears to be the language in which the deepest truths about reality are written. This raises what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical concepts correspond so precisely to physical reality? Why should the universe seem to operate according to mathematical laws? Some theorists, like Max Tegmark, suggest that this correspondence exists because mathematics and physical reality are the same thing. The universe, literally, is a mathematical structure. Others propose that mathematics describes fundamental, logical relationships that any possible reality must satisfy. But this still leaves us with the question, why should reality be logical or mathematical at all? Why shouldn't there be chaos instead of order, randomness instead of pattern? As we push against these ultimate questions, we also encounter the limits of what science can tell us. Science is extraordinarily powerful at describing how things work, at making predictions, at revealing hidden patterns and connections. But there may be some questions that lie beyond the reach of scientific methodology. The question of what existed before the Big Bang might be one of these questions. If time itself began with the Big Bang, then the concept of before might be meaningless. If our universe is causally isolated from whatever preceded it, then we might have no way of gathering evidence about pre-Big Bang reality. This doesn't mean these questions are worthless. They push us to think more deeply about the nature of reality, time, causation, and existence. They stretch our conceptual frameworks and challenge our assumptions. Even if we can never definitively answer them, the process of thinking about them teaches us something important about the universe and ourselves. One of the most remarkable things about our current moment in history is that these profound questions about the origin and nature of reality are not confined to a small group of specialists. Thanks to advances in education, communication, and scientific literacy, millions of people can engage with these ideas and contribute to the ongoing human effort to understand our cosmic situation. You, watching this video, are part of this grand endeavour. Every time you think deeply about these questions, every time you're filled with wonder at the vastness and complexity of existence, you're participating in one of the most noble and ancient human activities. The quest to understand where we came from and why we're here. You might wonder what practical difference it makes whether our universe emerged from quantum fluctuations or brane collisions or eternal cycles. These theories seem so abstract, so removed from daily life that they might appear to be merely academic exercises. But throughout history, the most abstract and theoretical discoveries have often led to revolutionary practical applications. Quantum mechanics, which seemed bizarre and irrelevant when it was first developed, now underlies computer technology, medical imaging, and countless other practical applications. More importantly, these theories change how we think about ourselves and our place in the cosmos. If we're part of an infinite multiverse, it might make us feel less central, but more connected to an infinitely creative cosmos. If consciousness plays a fundamental role in reality, it might make us feel more responsible for the kind of world we create through our observations and choices. Carl Sagan wrote about the pale blue dot, our Earth as seen from the edge of the solar system, a tiny speck suspended in the sunbeam. He argued that this cosmic perspective should inspire humility, cooperation, and care for our planet and each other. The theories we've explored today extend this perspective even further. If our entire universe is just one bubble in an infinite multiverse, or one cycle in an eternal series, or one computation in an endless algorithmic process, then our cosmic insignificance becomes even more profound. But paradoxically, this might make our existence more precious, not less. If consciousness is rare in the cosmos, if the particular arrangement of matter and energy that creates our thoughts and experiences is unlikely and temporary, then every moment of awareness becomes extraordinarily valuable. The fact that the universe has evolved structures complex enough to contemplate their own existence, that atoms forged in stellar cores can arrange themselves into brains capable of wondering about the origin of atoms, is perhaps the most remarkable thing of all. As we near the end of our journey, it's important to acknowledge that we've raised more questions than we've answered. Each theory we've explored opens up new mysteries, new puzzles, new frontiers for investigation. This is not a failure of science or philosophy. It's their greatest success. The most profound questions about existence don't have simple, final answers. They reveal layers upon layers of complexity and mystery, each more fascinating than the last. The question of what existed before the Big Bang may never be definitively answered. But in our attempts to answer it, we've discovered remarkable things about the nature of time, space, matter, energy, consciousness, and information. We've pushed the boundaries of human knowledge and imagination. We've connected the most abstract, theoretical physics with the deepest questions of meaning and purpose. Ultimately, the question of what came before the Big Bang connects to the eternal questions that have fascinated humans since we first developed the capacity for abstract thought. Where did we come from? Why do we exist? What is our purpose? How should we live? Science can't answer all of these questions, but it can inform our thinking about them. It can reveal the extraordinary nature of our cosmic situation. It can show us that we're part of something much larger and more complex than previous generations ever imagined. Whether our universe is eternal or temporary, whether we're alone or part of an infinite multiverse, whether reality is fundamentally physical or informational, in all cases, the emergence of consciousness capable of asking these questions is remarkable. You are a temporary arrangement of atoms that the universe has used to contemplate itself. Through your thoughts and experiences, the cosmos becomes self-aware. In a very real sense, you are the universe thinking about its own existence. This brings us to our final section, a reflection on what all of this means for how we should think about our existence and our future. We began this journey with a simple question: what happened before the Big Bang? Now, after exploring the furthest reaches of theoretical physics and cosmology, we find ourselves in a place that's both humbling and inspiring. surrounded by mystery, but armed with remarkable tools for thinking about that mystery. Let's take a moment to reflect on the extraordinary ideas we've encountered. We've seen how our universe might be part of an eternal cycle, dying and being reborn infinitely through time. We've explored the possibility that we're just one bubble in an endless cosmic foam, with new universes constantly being created around us. We've considered that our reality might have emerged from collisions in higher dimensional space, or that it spontaneously created itself from absolute nothingness through quantum mechanical processes. We've even entertained the idea that existence itself is fundamentally informational or computational, and that consciousness might play a deeper role in creating reality than we ever imagined. Each of these theories is remarkable in its own way. Each opens up vistas of possibility that challenge our everyday understanding of what it means to exist. And yet, none of them provides a final, complete answer to the question that started our inquiry. Perhaps that's because the question itself has evolved as we've explored it. We started by asking what happened before the Big Bang, assuming that before was a meaningful concept. But we've discovered that time itself might have begun with the Big Bang, making before potentially meaningless. We've also discovered that the question, what happened before the Big Bang, is really a stand-in for deeper questions. Why does anything exist at all? What is the ultimate nature of reality? How did complexity and consciousness emerge from whatever fundamental processes govern the cosmos? These questions don't have simple answers, because they're not simple questions. They probe the deepest mysteries of existence itself, and it's entirely possible that they will continue to challenge human understanding for generations to come. There's something profound about living in an era when we know enough to ask the right questions, but not enough to answer them definitively. We're poised at the edge of knowledge, able to see into the depths of the mystery, but not yet able to fathom them completely. This position is both frustrating and wonderful. It's frustrating because we want answers, closure, certainty, but it's wonderful because it means we live in a universe that's genuinely mysterious, genuinely surprising, genuinely worthy of our sense of wonder and awe. The physicist J.B.S. Haldane once said, "The universe is not only stranger than we imagine, it is stranger than we can imagine." Our exploration of pre-Big Bang theories confirms this insight. Reality appears to be far weirder, far more complex, and far more interesting than our everyday experience would suggest. One of the most remarkable aspects of our current moment in history is that these profound questions about the ultimate nature of reality are no longer confined to a small elite of philosophers and scientists. Through education, communication technology, and the inherent human capacity for wonder, millions of people can engage with ideas that would have been incomprehensible to most humans throughout history. You, right now, thinking about these concepts, are participating in humanity's greatest intellectual adventure. You're using a brain that evolved to help your ancestors find food and avoid predators to contemplate the origin of space and time itself. This is one of the most extraordinary things that has ever happened in the known universe. While these theories might seem abstract and removed from daily life, they actually offer profound practical wisdom. When you truly grasp the scale of cosmic time and space, when you understand that our entire observable universe might be just one tiny bubble in an infinite multiverse, it changes your perspective on what matters. The petty conflicts and anxieties that dominate much of human life begin to seem less significant when viewed against the backdrop of cosmic time. The things that truly matter consciousness, beauty, love, creativity, the quest for understanding stand out more clearly. This doesn't diminish the importance of human life and human concerns. If anything, it makes them more precious. If consciousness is rare in the cosmos, if the particular arrangement of atoms that creates your thoughts and experiences is unlikely and temporary, then every moment of awareness becomes extraordinarily valuable. Some of the theories we've explored suggest that consciousness might play a fundamental role in determining which possibilities become real. Whether or not this is literally true, there's a metaphorical truth here that's worth considering. We are the part of the universe that has become aware of itself, and with that awareness comes responsibility. We are the means by which the cosmos contemplates its own existence, questions its own origins, and perhaps even influences its own future evolution. This is both a tremendous privilege and a tremendous responsibility. How we use our consciousness, what we choose to focus on, what questions we ask, what values we embody, might have implications that extend far beyond our individual lives. If consciousness is indeed rare and precious, then every conscious being becomes a steward of something sacred. The quest to understand what existed before the Big Bang is far from over. New theoretical developments in physics, new computational tools for modelling complex systems, and new observational technologies for studying the cosmos will continue to provide fresh insights into these deep questions. Future generations may have access to evidence and theoretical frameworks that we can barely imagine. They might be able to detect signatures of other universes or prove that consciousness plays a fundamental role in physics, or discover that reality is indeed computational at its core. Or they might discover that we've been thinking about these questions in completely wrong ways, and that the true nature of pre-Big Bang reality is something we haven't even conceived of yet. But even if future science provides more definitive answers about the physical origins of our universe, the deeper philosophical questions will likely persist. Why is there something rather than nothing? What does it mean for something to exist? What is the relationship between consciousness and reality? These questions have fascinated humans for thousands of years, and they will likely continue to fascinate us for thousands more. They connect us to the deepest mysteries of existence and remind us that for all our scientific progress, we remain finite beings contemplating infinite questions. There's something to be said for living in a universe that maintains its mysteries, even as we learn more about it. A completely explained universe might be a less interesting universe. The fact that reality continues to surprise us, continues to challenge our assumptions, continues to reveal new layers of complexity and beauty. This is part of what makes existence worth contemplating. The mystery of what came before the Big Bang joins the mysteries of consciousness, of quantum mechanics, of the nature of time, and countless others that keep the universe interesting and keep us humble before the vastness of what we don't yet understand. As we conclude this exploration, I want to extend a personal invitation to you. Don't let these ideas remain abstract intellectual curiosities. Take them into your daily life. Let them change how you see yourself and your place in the cosmos. The next time you look up at the night sky, remember that you might be looking at the result of processes that have been unfolding for infinite time. Those stars might be just the latest chapter in a story that has no beginning, or they might be part of one tiny bubble in an infinite foam of universes, or they might be the product of collisions in dimensions you can't perceive. When you experience a moment of consciousness, when you're aware that you're aware, remember that this might be the universe coming to know itself through your experience. Your thoughts and feelings might be more cosmically significant than you ever imagined. When you face challenges or uncertainties in your life, remember the vast scales of time and space we've discussed. Remember that you are a temporary arrangement of atoms that somehow has become capable of love, creativity, and wonder. In a cosmos that might be mostly empty space and dark matter, you represent something extraordinary. The question of what existed before the Big Bang is really a question about our origins, our nature, and our destiny. It's part of the larger human project of understanding ourselves and our place in existence. This project began when the first humans looked up at the stars and wondered what they were. It continued through thousands of years of mythology, philosophy, and religion as we tried to make sense of our cosmic situation. It accelerated dramatically with the development of modern science as we developed tools for probing deeper and deeper into the nature of reality. And it continues today with you as you think about these ideas and grapple with these mysteries. You are part of a chain of inquiry that stretches back to the origins of human consciousness and forward to whatever discoveries and insights await future generations. Some people worry that the cosmic perspective diminishes human meaning, that if we're just tiny specks in a vast universe, then our lives don't matter. But I would argue for exactly the opposite conclusion. The fact that this vast, ancient, complex cosmos has given rise to beings capable of understanding it, loving it, and finding it beautiful is perhaps the most meaningful thing of all. You are not separate from the universe, looking in from the outside. You are the universe becoming conscious of itself. Every act of understanding, every moment of wonder, every expression of love or creativity is the cosmos celebrating its own existence through your experience. In this sense, your life is not insignificant against the cosmic backdrop. It's an integral part of the cosmic story itself. So what existed before the Big Bang? After all our exploration, the honest answer is we don't know. We have fascinating theories, compelling possibilities, and remarkable insights into the nature of time, space, matter, and consciousness. But the ultimate mystery remains. And perhaps that's as it should be. Perhaps the most important thing is not to solve the mystery, but to remain worthy of it, to maintain our sense of wonder, to continue asking deep questions, to keep pushing against the boundaries of what we can know and understand. The universe has spent 13.8 billion years evolving the capacity to ask questions about its own origins. The fact that you can think about what came before the Big Bang is itself one of the most extraordinary developments in the known history of the cosmos. I'll leave you with this thought. Regardless of what existed before the Big Bang, whether it was eternal cycles, infinite multiverses, higher dimensional collisions, quantum creation from nothing, or something we haven't even imagined yet, the fact remains that here you are, thinking about it. In a cosmos that might be mostly empty space, you represent complexity. In a universe that might be mostly unconscious matter, you represent awareness. In a reality that might be fundamentally random, you represent the search for meaning and pattern. You are simultaneously cosmically insignificant and absolutely irreplaceable. You are the universe's way of experiencing wonder at its own existence. And that wonder, that capacity for awe in the face of mystery, might be the most important thing that has ever emerged from whatever processes gave rise to our reality. The question of what came before the Big Bang remains open, waiting for future discoveries and insights. But the fact that conscious beings exist to ask the question, that the universe has become capable of wondering about its own origins, is already an answer of sorts. It tells us that whatever process gave rise to our cosmos, it was creative enough, complex enough, and rich enough to produce minds capable of contemplating infinity. And in that contemplation, in that wonder, in that ongoing quest to understand our deepest origins, we find something that might be more valuable than any final answer. We find ourselves participants in the greatest mystery story ever told, the story of existence itself. Thank you for joining me on this journey to the very edge of human understanding. The universe is stranger and more wonderful than we ever imagined, and the greatest adventures in discovering just how strange and wonderful it is still lie ahead. Keep wondering, keep questioning, keep looking up at the stars and remembering that you are made of star stuff, thinking stellar thoughts, participating in the cosmic awakening that began billions of years ago and continues through your consciousness right now. The mystery of what came before the Big Bang is also the mystery of what comes after, and you are part of writing that continuing story. If this exploration into the deepest mysteries of existence has sparked your curiosity, I'd love to hear your thoughts in the comments below. Which theory about pre-Big Bang reality do you find most compelling? What questions does this raise for you about consciousness, existence, and our place in the cosmos? And if you enjoyed this deep dive into the ultimate questions about reality, please consider subscribing for more explorations into the frontiers of science, philosophy, and human understanding. Together, we can continue humanity's ancient quest to understand where we came from and why we're here. Until next time, keep wondering about the magnificent mystery of existence. And remember that in doing so, you're participating in the universe's ongoing journey of self-discovery.